Thanks so much. I'd like to thank the organizers for the invitation to such a great conference. And today I'm going to describe an emerging picture of the ends of the Hitchin moduli space. And in particular, I want to describe how wild Hitchin moduli spaces appear. So thematically, my talk is most related to Andy Kneitzke's talk from yesterday and Jan Swoboda's talk, who's going to be next. So it's kind of in that same triple vein. Just a fixed notation. So the fixed data of a Hitchin moduli space, for people who don't think about them quite so regularly, will be C, a compact Riemann surface of genus G. We'll take G bigger than 2. Oh, right, I'm not supposed to touch this. Our structure groups will be SUN and its complexification, SL and C. And we'll take E, a complex vector bundle of rank N. And for simplicity, we'll just also have it be degree D. And from this fixed data, we're going to get a Hitchin moduli space. So, let's go here. So the points of the Hitchin moduli space are Higgs bundles. And so we have this equivalence between polystable Higgs bundles on one side and I'll consider this a pair of a holomorphic structure on the bundle, which makes it a holomorphic bundle and a Higgs field phi. So this Higgs field is a 1-0 form on C, valued in the endomorphisms of E, the traceless endomorphisms. So this is just some matrix valued 1-0 form of the Higgs field. And we're going to impose an additional condition such that this should be holomorphic. And this is the first of 2 Hitchin's equations for Hitchin. And Hitchin and Simpson proved that given any the algebraic condition of stability was enough to guarantee the existence of a special Hermitian metric on E. Solving Hitchin's equations. So this will be a triple now of an additional Hermitian metric. On E, and it's going to solve this equation. So this first bit, using the same kind of style of notation as Andy, this is the curvature of the Chern connection, the unique connection whose 0-1 part is del bar of E, and that's unitary with respect to H. And this is the adjoint with respect to H. So you have a 1-0 form and a 0-1 form. So this whole thing is a 1-1 form. And this will be the second equation. And this is a coupled system of nonlinear PDE, and it's kind of second order with respect to the metric. And so we can do all this up to gauge. On the one side we have SL E, and then once we fix the metric, we have SU of E, and this will be the Hitchin moduli space M. So you don't need too many facts about the Hitchin moduli space for this talk. The most important, just two. So the first fact is that M is non-compact and it's hyperkähler. So I want to, and the whole reason why we're considering solutions of Hitchin's equations rather than Higgs bundles is that you need to understand this H if you're going to understand the hyperkähler metric on the Hitchin moduli space. And the second fact is the existence of this, I'm going to put it over on this board so I can make reference to it later, just because of the centrality of these spectral data, is this Hitchin fibration. So given any point in the moduli space, there's a map to the base, to a vector space, which just sends this to its eigenvalues of the Higgs field. And so what this looks like, if we kind of draw it projectively, so this is a vector space, which I've just drawn the line at infinity, the sphere at infinity, and generically the fibers are compact complex tori. I'll draw two because they're generic. And then there's a complex codimension 1 locus over which the torus fibers degenerate. Can you see the difference? This is orange and this is white? Okay. So the place, just call it B prime. This is the regular locus, where the torus fibers are tori, and then we'll have the singular locus, which is this stratified over which things degenerate. And so we can also consider the regular locus up here. So there's this spectral data. Where from the data of the eigenvalues of the Higgs field, we're going to give a spectral cover. So the Higgs field is just it's just an n by n matrix, value 1-0 form. And so above, given any point in your curve, C, you get generically n distinct eigenvalues, which can do some interesting stuff as you move through. So sometimes they collide. And so we're going to define Z. The interesting points for us will be this ramification locus, where you have the mixing of eigenvalues. And I'll just use the notation this. It's an n-to-1 cover. And these points here will be Z tilde. So, right. So in the rank 2 case, this is particularly in the rank 2 case. It's easy to say what's in the regular locus. It's in the regular locus if and only if the determinant of the Higgs field has only simple zeros. If and only if the spectral curve, which is now a 2-to-1 cover, is smooth. And so this picture is right, that kind of the regular locus is where the spectral cover is smooth, and the singular locus is where it's not. And this, the first and third equivalents, they work for general n. Talking about what's simple is slightly harder. You can use the discriminant, but there's a slightly more general condition there too. Okay, so the big goal in this talk actually no, sorry, not the big goal in this talk, just the big goal that we're kind of, that everything is moving towards is to describe the asymptotic geometry of M. Which Jan will talk about. But a first and important step in all of this is to describe solutions of Hitchin's equations near the ends of the moduli space, so far out, kind of near that boundary circle. Okay. Near the ends. So I'll draw but we're going to restrict ourselves to the regular locus in this talk, and then for the first half, and then kind of in the second half, I'll talk about what changes when you go to the singular locus, and this is any rank. So what we're going to do is we're going to fix a Higgs bundle in the regular locus. And what we're going to do is we're just going to take the line. We're going to consider the R plus family parameterized by T, where we just scale the Higgs field up by T, and we're going to consider the associated solution of Hitchin's equations, the Hermitian metric HT. So over here in this picture, here's our array. Oops, slightly more space. So this is intersecting kind of, this is fibered over some line here. So we're going to consider this family. And what happens at the ends is that as t goes to infinity, the curvature of the Chern connection, it concentrates at these points, these ramification points. And so you can ask what the limiting metric H infinity looks like. So H infinity is the push forward of a Hermitian-Einstein metric on a certain line bundle, which I'll say just a word about. On the line bundle L over the spectral cover. So so we encoded the data of the eigenvalues of the Higgs field in this geometric data of the spectral cover, given by a point in the base. And what do these points in the tori represent? Well, these are actually the prim varieties of the points in the base. So this is prim of the associated spectral cover. So each point in here represents a different line bundle on the spectral cover, and that line bundle, what it encodes is the eigenvalues, the eigenspaces. Like that, it's the eigen line bundle of the Higgs field where you associated to each eigenvalue. And so this, you get a whole eigen line that's swept out. And so H infinity is the push forward of a Hermitian-Einstein metric on that line bundle. This Hermitian-Einstein metric is singular at Z. H infinity is singular at Z, so the Hermitian-Einstein metric is singular at Z tilde, And so there's some boundary conditions that are determined by some choice of parabolic weight, -1/2 there. But this is nice. When people say that Hitchin's equations abelianize, this is one of the things that they mean. So why is this the first step towards describing the asymptotic geometry of M? So from triples, if you consider so if you take h infinity rather than the metric ht on triples, you actually get another hyperkähler metric. On M prime. And this is the so-called semi-flat metric that Andy talked about yesterday. And this metric does not extend to M. So this is just a natural metric existing in any complex integrable system like we have over here. These torus fibers are half-dimensional. And this is it's called semi-flat because it's flat on these torus fibers. And on the base, it's a special Kähler metric. So the conjecture for the relationship between the semi-flat metric and Hitchin's hyperkähler metric, this is definitely a weak form of Guyota-Moore-Kneitzky. Rather than the strong integral relation, is that Hitchin's hyperkähler metric, GL2, differs from the semi-flat metric, GSF, by terms that are exponentially decaying in kind of this direction T. And so this, so the first step to prove this conjecture, to prove this conjecture, which I'm not going to do. The first step is to understand HT, which gives Hitchin's hyperkähler metric, kind of versus H infinity, which gives a semi-flat metric. And so this brings us to a discussion of the ends of the moduli space. Okay, so any questions while I move the boards?
Actually, the branch locus, if you're taking this expansion, is also moving out to infinity. Typically.
Oh, right, you can rescale the Higgs field. Oh, sorry, you can rescale the spectral cover so it doesn't.
Okay, so but it's still accumulating at the branch locus and not at the intersections of the zeros.
Mm-hmm. Okay, so actually I'll do this over here. To start. So what's the strategy to describe HT? So we're going to start with H infinity. This is a metric which is singular at Z, so let me draw a picture. Here's C, here's Z. I'm implicitly drawing the rank 2 case where you have 4 simple zeros. So here's the points of Z, and I've drawn this where the curvature has a delta function spike. So then we have a second ingredient, which are some smooth solutions, HT model. So these solutions actually exist on the whole complex plane. And And unlike H infinity, which is singular, they kind of are little bumps that live in the middle of the plane. As t goes increases, you get higher and higher, more concentrated. The width scale gets smaller. And what we're going to do is we're going to take this bump and we're going to pick it up and we're going to glue it in on a neighborhood here. Just pick it up right there. So we're going to glue these two together. It's just an outline to get HT approximate. So inside of some kind of little disk, it'll be exactly equal to HT model. Outside, it'll be exactly equal to H infinity. Both of these are actually solution of Hitchin's equations. But on this gluing region, on some annulus, you fail to be a solution of Hitchin's equations. But it's really close to solving it. And then the last step, kind of the analytical step, is to perturb to HT from this HT approximate using an implicit function theorem. So I want to say kind of just a piece. I want to focus kind of on the model solutions, and I'll state the result for 4. Because these model solutions, like I said at the beginning, I want to talk about these wild Hitchin moduli spaces, and they first appear here with the model solutions. Okay. So about the second point, number 2, about the model solutions, is near kind of any point Z where the ramification locus, there exists some coordinate and a gauge, coordinate Z and some gauge, in which you can make the Higgs field. It's a holomorphic gauge, so del bar E is just del bar. This looks like this. So you see that the determinant of this is negative z dz squared. So you really have a simple 0 in your determinant. And H infinity, we can further pick the gauge. So that H infinity looks like this. And this uniquely determines the gauge once you've made H infinity look like that. So like I said, as t goes to infinity, the curvature concentrates. So I want to describe how you can recover a model solution. So we have t, and here's infinity. So on some little disk, to start with, your ht looks something like this, and then as you go a little farther out, it gets more concentrated, and then at infinity, it's fully concentrated at the point. So this kind of the width scale, is something like t to the negative 2/3. And so you could actually zoom in. You can pick your rescaling parameter in order to make the width just 1 in all of these things. And so here you'd have the same picture. And then here, you get a lump. And then at infinity, when you've rescaled this to 1, you've extended to the entire complex plane C, and you get a nice, smooth little solution. And this is the model solution. So the first point I want to make is that the model solution you can actually recover just from a family HT going to infinity. That this isn't something that's just comes out of nowhere. And then the second thing is that I actually can write down the model solution explicitly. Right, so the whole problem why this was singular was that this, you have these, this is singular. So we can desingularize this. The model solution is actually radially symmetric. And what is it? So ut of z, it's like -1/2 log z. So it fully cancels this, this singularity. There z equals 0, and it decays as z goes to infinity. And it solves just an ODE. This solves this Pan-Lavey 3 type. ODE. So this is the model solution. And just to say how do you get this approximate solution, you can see you just add a cutoff function. Chi to interpolate, all we have to do is turn this u of t to 0, and then we're back on h infinity. So that for the approximate solution, if I wanted to make this ht approx, I would just add a chi here and a chi here. Okay. To say just a little bit about the perturbation. Oh yeah, any questions again while I move some boards? Yeah.
So are you saying that you can prove a priori that the rescaled solutions approach a limit solution which you're calling the model, and that limit solution satisfies the equation, and then since there's a unique solution to the equation, then that has to be that one? Or does that, or does these facts come sort of a posteriori after you've proven the approximation?
Yeah, they come after the approximation.
You don't know if it would be possible to sort of a priori prove that without knowing the approximation. That makes sense.
Right. Yeah. No. Yeah, I'm not sure how to do that. Right. No. I mean, yeah. I mean, the way that we actually did it is we wrote down the model solution, and then we glued it in and said, "Oh, this is a good guess." But yeah.
You don't know whether you can a priori prove that.
No. Yeah. No. It's too bad. That'd be nice. Yeah.
Is there a uniqueness at least of the solution? I mean, if you knew that it did approach a limit, then
Oh, a what?
Is there a uniqueness if you could prove that it did approach a limit? Then would you know that the limit has to be that one?
Yeah, I think yeah.
So it's just a question, of proving that the limit is.
Right. I mean, you do need to do something. Right. With this H infinity, you really need to pick kind of the right gauge. I mean, there's a lot of bad gauges, sort of, where it wouldn't converge to this. But as long as you like fully control the gauge. Oh yeah, you need decay estimates at infinity. Like you don't want anything that's. But as long as it's going, the curvature is going to 0, kind of near the boundary. This is the one that you end on.
I think Taubes and Mochizuki do prove the existence of the limit.
But they don't construct the, Mochizuki doesn't construct the model solution in the middle. I mean, he talks about that somewhere else. But yeah, he's mostly picking up the data of H infinity. And later in their talk, there's some places where, like if you look at his paper, he's losing a lot of information because he's not distinguishing model solutions that he should. Well, I mean, he didn't need to. I don't want to say should. Other questions? Okay. All right, so for the perturbation step, I'll just state a theorem, which I'm happy to state and conveniently also helps Jan out in his next lecture. So the question is, how is this HT approximate related to the actual metric? Okay. Oops. T, then some T naught. Okay, so this, oops, I'll state this. This is due to Mazzeo-Swoboda-Weiss-Witt. In the case SL 2014, in the case SL2C. And the case SLNC. So the statement is, let me draw a picture first. So you have this family. And so the HT gets exponentially close. The HT is close to HT approximate in the following sense. So for T, some large T, there exists some M such that when T is bigger than this cutoff T naught, HT is in this, this decaying cone. There exists a unique gamma of T such that the norm of gamma of T, which we're measuring, this Sobolev space, decays like T to the negative M, so it's good that M is positive here. Oops, positive. And the second thing is that this gamma is related to this in something like this sense. I want to say that this is schematically true, but not actually true. All of this is proved in unitary gauge, which means that the expression is actually more complicated. But this is really the idea, is that these differ by this e to the gamma of T, which is going to 0. And Mazzeo-Swoboda-Weiss-Witt, this theorem is one of the starting points for their more detailed analysis of the asymptotic metric of the moduli space. So this is kind of the end of what I wanted to say about the regular locus, and I kind of wanted to move on to the moduli spaces of model solutions. So what happens? This is all when we restrict to M, the regular locus where the spectral cover is smooth, and I want to say kind of what happens, what goes wrong, or what's the difficulty? How would you extend this to the rest of the Hitchin moduli space, which is something that's in progress, but I can tell you about these model solutions to start. Okay. Okay, so while I'm erasing this, I'll say that one thing that goes bad as you go to the regular, the singular locus is that the spectral cover becomes smooth. Sorry, it becomes singular, and so you have to deal with the metric H infinity itself. Mochizuki has done this. But then the other piece is this desingularization step, and this is what I want to talk about. And this is based with Andy Knightsky. In this paper, and also Steve Ryan. But what I'm going to say is not actually something that sort of is the focus of either paper. It's more, I'm just trying to pull the stuff out of those papers that's relevant to sort of this story about the ends of the Hitchin moduli space. Because this paper was actually about some correspondence with some W algebra representations. So what's new? This is not in the regular locus. And so the answer is in the construction of HT approximate. You need new model solutions. And actually what you need is moduli spaces. Moduli spaces of model solutions. So I want to start by making sort of two cases for why you get moduli spaces of model solutions. Because right up there you have your single model solution, which is great, but that's not the case in general. So the first motivation for why you might need moduli is I want to talk about this case of the colliding simple zeros. Simple zeros and M SL2C, just in the rank 2 case. So suppose we have our curve C, and we have two zeros which are staying kind of far apart. But what I want to do, I'm just going to draw this in the base. So here's the base, the Hitchin base. And suppose you took some Higgs bundles up here that projected kind of down to not a ray, but there's no reason not to take just some sort of some curve, which is kind of asymptotic to this. So what this would look like is that there's some sort of disk where you have two zeros, and as t goes to infinity, these are getting close. So let me draw kind of the picture of what you get there. So here I'm using this just kind of, just like up there, kind of formally, that there's some sort of reality that you hit. So you start with just the two disks, the two zeros, and you have your solution of Hitchin's equations. And then you can again, they get closer as t goes to infinity, and then they eventually collide. You can look at the curvature concentrating. And again, you can kind of rescale to width 1. And if you rescale so that the separation between these two is 1 at all scales, then you're actually going to end up on a solution there too. And so what you get is this is a solution here on the plane. So this is a little formal right now. I mean, you see that you can at least get zeros that are separated, even by taking kind of rays that are asymptotic. So we don't need to just consider things where the determinant of the Higgs field is some higher zero. This is not just z squared, but this is actually z squared plus u, dz squared, that's showing up. And this is a moduli parameter. Though some people will actually fix this one. So the second kind of a more rigorous motivation is just this, is what'll come next. I guess I have to move the boards again. Can everyone see all the 3 boards? Okay. So the second motivation for the moduli spaces is you can actually, this thing I'm erasing, darn, I should have looked. So originally, in the simple 0 case, there was a single holomorphic gauge that you could put everything into. But if you go from a simple 0 in the rank 2 case just to a higher order 0, there's not just a single local holomorphic gauge. All right, so suppose that near a point P, you have a simple 0 in your determinant of phi. So the negative determinant of phi, you can find some coordinate where it's z to z squared. Then there exists a holomorphic gauge in which phi is equal to this. All right, I'm not going to go too far. So here's the case of the simple zeros. In the case of the double 0, now that we've kind of argued for some parameters, suppose the determinant looks like z squared plus u. I'm omitting the constant term because you can always choose that the zeros have like center of mass centered at the origin. So you can just move that to get rid of that constant. Then the Higgs field, you see some very kind of minor things. Where you get these 2 constants on the diagonal. That means that when u is equal to 0, that there's 2 distinct things. There's z1, 0, negative z, and there's z0, 0, negative z. So you have the diagonal and kind of this not quite diagonal thing. But the interesting one, which will be kind of the basis of the rest of the next bit, is the case of the triple 0. Yeah. And here you have 2 kind of distinct cases. So you have this thing, which basically we're going to get a moduli space, and this will be the Hitchin section. And then you have the rest of the moduli space, or all right, plus u minus gamma squared. So you get this or this with the condition dz, with the condition that w cubed. So we just need the condition to be that this is actually a polynomial. So w just needs to divide this. So that's w squared plus u minus gamma squared. And lo and behold, you get an elliptic equation. And so I want to draw a picture of this. So what you see here, just looking at local holomorphic gauges, is you see this moduli space that I want to call the moduli space M23. So this will be a fixed piece of data for the moduli space, and this is going to be allowed to be varying. So our base will be parameterized by u and c. So we'll have a one-dimensional, this is a 4-dimensional moduli space with a complex one-dimensional base. And you see that over kind of every fiber, you have an elliptic curve. And the way that this enters this is the point at infinity. And so this is, right, so this is kind of exactly what you normally expect to see with the Hitchin moduli space. And so I kind of want to talk about these moduli spaces next. You also see, I want to point out that you see a stratification of the Hitchin moduli space, even here. This is similar, this is basically a Bielnicki-Berula stratification of the moduli space. You could say more about that. So, questions so far? Oops.
Are you saying that if you choose different curves that go to infinity that are asymptotic to the same thing, that for different curves you'll get different points in the moduli?
Yeah, exactly. So what I'll say at the end is that we're
so it wasn't a good idea to just choose array?
No, choosing array, you lose a lot of, or you lose data that you, you may not need it, but let's see, so this is the back one. Wait, that's the middle one. Okay. Yeah, so this is not like just a radial completion or compactification of the moduli space. This is kind of a compactification to this manifold with corners, which I'll say. That's just the emerging description, which I'll say a little bit about at the end. So, oops, that's my page number. So we're going to fix k and n co-prime. So I want to just, for right now, avoid the case of these double zeros, which and if you fix k and n co-prime, you can get this moduli space and some parameters, lambda. You get this, what we call the moduli space of SLKC Higgs bundles. The way I was describing this, it was on C, but it'd be better to describe it on CP1 with a marked point at infinity. And so this is the moduli. It's a moduli space of Higgs bundles with eigenvalues that have some growth condition. This isn't how you actually define the moduli space, but this is. I want to point out that when k and n are coprime, these eigenvalues are ramified at infinity. And this is a wild Hitchin moduli space. Meaning that this pole at infinity is not a simple pole, it's a higher order pole. And in some sense, it's a fractional pole of dimension k minus 1, n minus 1. So you see this case, the first case, the simple zero, is the case of M21. And sure enough, that's a zero-dimensional moduli space, so there's no moduli. But this triple zero case is a complex two-dimensional moduli space, which I've actually written it all out here, up to the deal of writing out the parabolic, underlying parabolic bundles. So this isn't the, for the sake of time, I won't say too much. So the definition of this MKN is actually, it's more subtle. So you don't just prescribe the growth of the eigenvalues like this. You actually have to fix some sort of, you need to fix some sort of irregular type. So Bicard and Bolch, actually I write out the irregular type, that you normally just fix that near some pole, what you see is that you fix this data just completely, where these TIs need to be diagonal. And then this is just kind of the data from the simple pole. So this behaves totally different from this. This is just fixed. This is the weighted flag data, and then you allow holomorphic variations. So this is data of your moduli space. But for these ramified things, the Higgs field will never diagonalize near infinity. It actually diagonalizes on some ramified cover. And so Andy and I, we defined the moduli spaces MKN. In that case, so we fixed the data on the ramified cover rather than down below, which meant that our moduli spaces are compact, while if you try to fix it down below to be some sort of skew thing, you get non-compact moduli spaces. So how does this actually help us? So from Ricard and Bolch, and also Mochizuki, you have a similar, so I mean, it's always going to be something about stable Higgs bundles, and some triple, but here we're going to have parabolic bundles. So we need to add some adjectives. These aren't just stable Higgs bundles, these are stable, good filtered Higgs bundles. This is a definition of Mochizuki, which means that they that on some local cover, local ramified cover, that these Higgs bundles diagonalize. And then if you have one of these stable ones, then you can get the same thing. There's a unique metric, Hermitian metric, solving Hitchin's equations. And the adjective we add here is adapted, meaning that the boundary conditions at infinity are fixed by are compatible with and give the same filtration as the filtration over here on the bundle. So I wanted to point out that this, I'm not writing that this is equal to the moduli space. This is true just purely at the level kind of points in the moduli space. And in the case of these good filtered things, this result of Mochizuki doesn't say anything about the moduli space itself. So how does this help us? So for us, basically, once you get one of these Higgs bundles on CP1 infinity, what this means is that using this, we can both get the data of HT model and H infinity. We could use this, haven't done this yet, to glue the right thing into these models. We can use this to glue the right thing into these where things are becoming singular. And so just the last, this is not very long, I just want to say, so what picture of the moduli space is appearing? So you see that these wild moduli spaces, they appear as the things that you're supposed to glue in. But you might ask, is there any way that you could see these moduli spaces kind of at the boundary of M itself? So that's just the last half board. So there's an emerging kind of conjectural description of the ends. And this is with Mazzeo and Swoboda and Weiss. And it's far out, but this is what expected. So there's nothing that we've done here. So we drew this picture originally. So the picture is, and then we do have the fibers here, but it's easier to draw it on the base, is that depending on the ray that you go out along, you can get different model solutions. And so actually what you should get is some sort of iterated real blowup of the space. So for like a double zero, you get something like this. For a higher order zero, you'd actually have a stratification, something like this. And that in this picture, the subspaces. If you take the union over all these parameters, these should appear kind of as faces of the boundary. So we're getting a compactification to a manifold with corners, conjecturally. And just to draw just a little better picture of this thing, how is this iterated? For dimensional reasons, I've always drawn this strata like this, but the singular locus is a stratified space. So suppose we're going out to the boundary, and this is a place where you have some triple zero. So you can think about this in the plane. You have 3 zeros, and there's going to be some sheets. There's cases where so you can bring all 3 zeros together, or you can bring 2 zeros together. And so these are all these double zero sheets where you have kind of a pair 2, 1. And so if this is the end at infinity, what this compactification should look like is something like, well, first you, there's different rates that these can approach each other as you go off to infinity. And if you take the slowest rate, you kind of blow up this intersection, and then you blow up this intersection. Oops. Depending on sort of, the rate at which these double zeros come together as opposed to the triple zero. And so this is the emerging, this is kind of where we're going, and thank you so much.